In this part of physics, we are going to talk about light mainly. And light, we're going to go through several points. First point, we're going to talk about optics, shadow, and light year. What is optics? Optics is a science or a branch of science that studies the properties and the behavior of light, regardless whether the light is a wave or a particle. So it studies just the light as the light is traveling through straight lines. So that means when the light, it deals with the light like it is a beam that is traveling in straight lines. And in optics, we are studying reflection, refraction, diffraction. So that means bending of light when it face wall or any medium in the front of it. So these ones are related to what? To optics. And one of the also of the applications of optics is the shadow. What is shadow? That means the person or the object prevents the straight lines of light from moving to the other side. So that means you have shadow on the other side of the light. So this is the first point. Second point is shadow. Why no one can precede his shadow? Because the light is very fast. How fast is the light? The light is traveling 300,000 kilometers per only 1 second. So it moves all that long distance in just 1 second. So if you are moving now, your shadow moving with this speed. So can you move in this speed as a person? No. So no one, a person or object other than light can move in this distance. So that means you cannot precede the light, the shadow of yourself, because the light of the shadow, because the shadow is moving in the speed of light, because it's as a result of light. So that means because its speed is very high. Okay, now imagine now this distance, which is 300,000 kilometers, is the distance that the light is traveling just in 1 second. If you see the Earth, you know how wide is the Earth. The Earth, all of it, its radius is about 6,000 kilometers. The radius of Earth is around 6,000 kilometers. Okay, imagine this distance now, 300,000 kilometers. If you compare it now with the radius of the Earth, it's gonna be around 50 times the radius of Earth. So this distance now, and this huge distance, the light is traveling this distance in just 1 second. Okay, what about the light now? How long? That means it's gonna travel in 1 hour. The light, how long it's gonna take to travel for 1 hour? That means how long the distance it will travel in 1 hour? If this one just in 1 second, what about if it is in 10 hours? What about if it is in 1 day? If the light is traveling for 1 day, how long it's gonna travel? Okay, what about a month? How long if the light is traveling for 1 month? How long the distance will be? If just this is the distance is only that is traveling in only 1 second. What about 1 month? What about 1 year? So the distance now that the light travels in 1 year is called light year. So what is light year? Light year is the distance that the light travels in a year. And it's a very huge distance. But in the universe, this distance is matter because we count it to find the difference between galaxies and planets and other things. So we can't count by kilometers because the distance there is very huge. So we use light year as a unit for long distance in the universe. Okay, that was for the first point, which is optics and shadow and light year, and you understand now these points. We'll go now to the next point. On this second point, we're going to talk about the colors of light and also the wavelength of these colors and how we see things, or objects or colors around us. Okay, light in general, the light that comes from the sun, or the light that comes from a white bulb or white lamp, or any white source of light. The light usually is a white color here as you see it. This white color now, it contains many colors. So the light that comes from the sun, it is white light, but it contains inside it many colors, but we don't see them. If we take this prism, and this one now is called prism, and we use it just to see the colors that the light color has. Okay, if you use this one now, and we put here the white color from the right side, what we'll see coming out from the other side? We're going to see the light itself, which is white here, is going to be dispersed into its main 7 colors, which is here, red, then orange, then yellow, then green, then cyan, then blue, then violet. These ones are the 7 colors that the white color of light has. And these colors now has different wavelengths. They have different wavelengths and they have different frequency. We don't see them, but we sometimes see them in rare occasions like the rainbow, or if we have a prism, or if you have some glasses that can disperse these colors. So in these occasions, just we can see them. But in real, what is around you in your home or in the way, you can't find these colors. Okay, now how if these colors now are contained in the light color? What is the effect of these ones? What is the effect of these colors? The effect of these colors is how do we see objects around us? How do we see objects around us? Okay, this color now, usually before some theories before, it used to say that we see objects because some particles or some atoms of that object move into our eyes. This is how some people used previously how we see things. But now, if we analyze it and understand how we see things around us, how we see them scientifically, what happens, why do we see them if there is light, but when there is no light, we don't see them? Okay, mainly these colors now and keep the order of them. I need to remember the order of these colors: red, orange, yellow, green, cyan, blue, violet. Red has the highest wavelength, while violet has the lowest wavelength. And also red has the least frequency, while violet has the highest frequency. That means violet has the highest frequency, and based on that, it has the highest energy. Okay, if we go to this picture here, it shows exactly how we see things. So the light, as we said, it contains 7 colors. When these 7 colors now are going into here, yellow ball, or any yellow color around us, how do we see things? For example, like the wall of a room, it's yellow. It's white, for example. How do we see it? Why? Because now all the colors of the light, when it gets to the wall, all of it gets what? Reflected. So when it gets reflected to our eyes our eyes then, by the analyzing of the brain, it tells us that this wall is white. So that means the white color reflects all the colors of the light back to the eyes. So we see this color white. Okay, what about if the color was red? What happens? If the color is red or blue or green or yellow, it absorbs all the colors of the light that are illuminated in that ball or in that red object, and only the red color itself is reflected. So as you see here now, only the red color is reflected from that object. So all the incident colors are absorbed except the color of the object itself, it was reflected. When it was reflected, then it comes to our eyes. So that means we feel or we understand that this color that we see it now is red. And same thing for other colors like green, like yellow, like blue. So that means blue color, how we see it blue? Because the blue color absorbs all the other colors and reflects only the blue color. So with the blue color or the reflected beam of the blue color, when it comes to our eyes, we understand that this is blue color. Okay, what about if it is black? If it is black, it absorbs all the colors. So none of the colors is reflected. When none of the colors is reflected, so we see this place like empty space. So then we analyze it, our mind analyze that this place, since there is no reflection, so that means it is what? Black. So usually some says that when you use your mobile, when it is black colors, so that means you get less beams reflected from the screen of your mobile to your eye. So that means it's much better for the eye. Okay, now just we give one example. If we have here a green color, if we have here a green color and white light is illuminated into that green color, how we see it green? As we said, because all the colors of the white light will be absorbed by that green color, and only the green color itself will be what? Will be reflected. So this now, this green color, when it is reflected to our eyes, we see this color what? As green. But now the question is, okay, this is now is a green color. This one now is a green color. If we just give it red color, if we give it only what? Red color, if we illuminate this green color by only red color, what color we will see the green color then? Will we see it green? It's green, but it's in a dark room. It's green like cucumber, it's green, but it's in a dark room. And just we illuminate this dark room by only red color. How will we see the color of the green or of cucumber or any other object? How will we see it? We're gonna see it black. Why are we gonna see it black? Because now this green color now will absorb the red. It will not reflect it. It will not reflect the red because the green color reflects only green. So that means you see like there is nothing is reflected from there. So you see it as what? As black color. We'll understand more with other pictures. Here now are the primary colors and the secondary colors. Primary colors in physics and in general in light are green, as you see it here, and red and blue. These ones are the primary colors. Any other colors are called secondary colors. And any other colors, that means they came from these primary colors. What are these colors that are primary? Green, red, blue. And these ones have to be memorized. I need to know them. Okay, now, red with green. Red with green here. As you see, red with green here now. they produce what color? Yellow. So yellow is primary or secondary color? No, yellow is secondary color. Okay, red with blue. Red with blue here, it gives you what? Magenta color. And here now green with blue, it gives you what? Cyan color. So we understand now that there are three primary colors that are red, green, and blue. And we understand also again that there are three secondary colors. What are they? Yellow, cyan, and magenta. Okay, then if we take these three secondary colors and we put them here, which are the magenta, yellow, and what? And cyan. These ones now, if we use them, they're going to produce again the primary colors. So that means if we mix yellow now with cyan, yellow and cyan, it will give us what? Green. Why? Because if you go to see the primary here, this is yellow. I'm going to make it red. This is yellow. And this is what? This is cyan. This is blue. This is yellow. And this is what? Cyan. And all of them, they are included inside what? Inside the green. So if you now mix the yellow with the cyan, and since both of them are secondary colors and they are inside the green, so when you mix them, they'll give you what? Green. Same thing now, if we mix here this color now, which is magenta, if we mix now magenta here and also with what? With cyan, it will give us what? The color that both of them are included in, which is what? The blue color. So you understand now primary colors what they give and secondary colors what they give. We understand now. But these ones now, how they are related to how we see objects. How we see objects. Look here now. Here now, this is green color. If we illuminate by using green color, if we illuminate what? I'm gonna use, okay, if we illuminate green color on blue color, how the beam will be reflected to our eyes? How will it be reflected? So that means we are illuminating blue color by using what? Green color, light. So the green color as light is illuminated on the object that is blue. How will we see the blue color of the object? We're going to see it what? Black. Why? Because this object now, which is the blue, it will not reflect the green object that comes to it. Okay, what about if we illuminate this blue color by blue color? How will we see it? Of course, the blue color will be reflected because the object that is blue reflects the blue beam or the blue light. So this blue light now is reflected to our eyes. We understand that it is what? Blue. Okay, what about if we now illuminate this blue color by using cyan color? What will happen? What will we see this object? So the object is blue and the light is cyan that is illuminated over the blue object. How will we see the blue object? What color will we see it? So we go now to see this cyan color is secondary or primary. I mean secondary or primary color. It is secondary color. And since it is secondary color, that means it contains two colors, two primary colors. What are these two primary colors? They are green and blue. So that means now green and blue light is traveling through this beam now as cyan light. When it comes now to this blue object, the blue object will reflect only the blue color. So that means this blue color then will be reflected as blue. So we're gonna see this object as what? As blue. Okay, what about if we give it now? What about if we give this object green color, red color? or yellow color? What about if we give it what? Yellow color. Again, make it yellow. So if we give it now yellow color as light, how will we see this blue object? So that means when the light is yellow, that means it contains two primary colors. What are they? Green and red. And that means what is traveling through this beam of light is green color and red color, but as light color. So that means, but it contains two, the yellow itself, it contains two primary colors, which is green and red. These ones now, when they come to the blue object will reflect only blue. So that means none of these lights will be reflected. Since none of these lights is reflected, so we're gonna see this blue object as black. So when there is no reflected beams of light from any object, we're gonna see this object as what? As black. So you understand now, how do we see objects around us and how colors or the light of colors, how do they affect the color of objects that we see them? Okay, and we understand more. How do we see or why do we see the sky as blue color? And why do we use red color for warning things, for traffic lights, and for the brakes lights of the cars? In the back of the cars, the brakes always, we use what? Red color. And for warning and on the high towers, we use red. Why do we use that red? And why do we see the sky blue? These things, we're gonna understand them in this picture now. Okay, just we need to see here now, the light that is coming from the sun, the light that is coming from the sun, this is now the light that is coming from the sun, or the spectrum that is coming from the sun. This now electromagnetic spectrum is called what? Electromagnetic spectrum. What does it contain? So the rays, the electromagnetic rays that comes from electromagnetic waves that are coming from the sun, what do they include? They include the following spectrum. They include radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. All that are coming from the sun. Okay, do we see all these ones? No, we only see the visible light. We only see the visible light. Other waves and rays, we don't see them. So we see only what is called visible light. And this visible light, we see it as, in general, we see it as white light. White light. Then this white light, as we said, if we disperse it by using prism, we're gonna see it includes what? 7 colors as here, which is red, orange, yellow, green, blue, indigo, and what? And violet. Okay, these now colors, they have different wavelengths as mentioned here. And this unit is in nanometer. So that means, as you see red, it has wavelength of 700 nanometer. While violet, it has what? 400 nanometer wavelength. That means now the wave of the red is long, while the wave of violet is what? Is small here. So that means now, why do we use red color on warning and traffic lights and also on the brakes lights of cars and many other important things? We use red. We didn't use other colors. Why? Because now, if there is dust on the air, there are particles as dust on the air now. When the indigo or the blue color moves in the air, it is collided with what? With dust particles. And since these dust particles, in general, they are the size of the what? Of the wave of that color. So this color then get what? Dispersed. Get what? Dispersed. So it cannot travel easily in the air since its wavelength is small, and it cannot overcome the dust particles that it faces easily. But now dust particles here for the red, you're gonna see the red is able what? To move over many particles. So that means in general, red particle is the least, red color is the least color to be what? Dispersed in the air. So that means it can travel longer distance and it keeps its movement. So that's why we use color red, because we can see it even if it is cloudy or like a dusty, or windy color. You can still see what? The cars that have red color when they slam their brakes, and also you still can see the important things like traffic lights or airports or other things that are important. Okay, second question now. Why do we see the sky blue? The sky in real, it's not blue. Some people will say because the sea is blue. The sea is looked blue because it reflects the sky color that is blue, not because the sea itself is blue. So sea is blue as a reflection of the sky. So mainly it's the sky. Why the sky is blue? So same thing now here. When these colors now are coming from the sun to the atmosphere of the earth, the atmosphere now and the particles in the atmosphere usually in the size of the other what here? Wavelengths. So usually these ones now, these colors, which is here, which is blue, indigo, and violet, they get dispersed a lot more than red and orange and yellow. So they get dispersed a lot in the atmosphere. Why? Because they have many collisions with the particles of the air. So they get dispersed a lot on the air. So which colors they are? Blue, indigo, and what? And violet. So yellow, in general, we don't see red color in the sky because the red color can move over these particles easily. So that means it's not dispersed in the sky. So we don't see the red color. But blue and indigo and violet, they get dispersed because they have many collisions with the particles of the air. As a result now, why just we see when these colors are dispersed in the sky, so we see these colors now, but why do we see just blue? We didn't see what? Violet here, for example. Because violet, the atmosphere is still able to absorb the what? The violet color. So it's generally, it's absorbed in the atmosphere. And also the eye, our eyes has more sensitivity to blue. So that means we see the blue since it becomes what? Dispersed like violet, but violet is absorbed, and we don't have that sensitivity to violet like what? Blue. So that's why we see the sky blue, because the wavelength of blue is less than the other colors, and it's dispersed in the air, so it looks like that place or the sky is blue. So you understand now what is the relationship between wavelength and the use in physics of light, and you understand the electromagnetic spectrum, what does it contain, and you understand that when we go from red to violet, wavelength decreases while frequency is the opposite, increases, and energy as well, it goes with the frequency. So that means now red has the least frequency and the least energy, while violet has the highest energy, highest frequency, but lowest what? Wavelength. So you understand now what are the visible colors, and we understand how do we see things in general, and we understand why we see objects black or red or whatever. So this is now we finished the second point in this part. We'll go to the third part, and the third part we'll discuss mainly 3 points. What are these 3 points here? So these ones are the 3 points that we're going to study now. We're going to understand now what is luminous flux, and what is luminous intensity, and what is illuminance. So these 3 words, we have to understand them completely, and what's the difference between them. And they are related to light, but they are not related just to light, to understand what is light. No, they are related to what is the amount of light we have in a room, what is the amount of light we receive from any source of light. So that means it's related to measurements, how to measure the amount of light you receive. So these 3 words are related to these ones. Okay, what is luminous flux? Luminous flux here, and its unit is lumen, and it's right LM, its unit. Luminous flux is the total amount of light that is coming out from a source of light. So this total amount of light that is coming out of a source of light, we call it what? Luminous flux. And luminous flux is measured by the manufacturing plants. So those who produce the lamps, they put these lamps inside a ball, and they get exactly what is the amount of light that this source can produce or can emit. So you understand now, luminous flux is the total amount of light that is coming out from a source of light, and its unit is what? Is lumen. So you understand now what is luminous flux, which is the first word here. Okay, what about the second one here now? We have luminous intensity, and its unit is candelas, and also the illuminance, and its unit is what? Lux. What's the difference between them? Both of them, luminous intensity and illuminance, both of them, they are units that gives you what is the amount of light that is received. But here now, luminous intensity, it's the amount of light that is emitted in a specific direction. The amount of light that is emitted in a specific direction. And it is mainly the amount of light that is emitted per the unit of what? Of solid angle. So this one is called solid angle. And solid angle here, it's the angle here that its radius here, its radii here, its radius here, from here, the source of the light to here. So that means now, this radius, if you make it a square, you're going to get the area of this part. So this part now, it has area. When the area of it equals the radius here squared, the radius of the distance between the source of light to this part exactly. So this one now we call, in this case, if this condition is applied, so we call this angle what? We call it what? Solid angle, and it is what? Stradium. It is what? It is a stradium. So one stradium, it means what? It means the area of a solid angle here that it makes when the radius of the angle is squared equals that part, or that area is squared. So that means now the flux, the luminous flux, if you divide it by how many angles like this here, it's going to give you what? The candelas. And one candela in general, it means the amount of light that one wax candle or one wax candle can what? Can emit. So this one is called what? One candela. So it's not used how many luminous flux or how much luminous flux is emitted towards the area in meters squared. It is just in what? In radian, which is the angle of solids. Okay, related to illuminance now. What is illuminance? Illuminance is similar to luminous intensity, but the difference now when you divide it here, the luminance will be, which is illuminance, which is E, it equals the P, and this one is P, which is the luminous flux is P, over the area of the sphere. So now this source now, imagine this source now is surrounded by a sphere, around it, by a sphere. What is the area of this sphere when all this light is divided into the whole sphere? That means the whole sphere, like 3D. The whole sphere now, you imagine this source now of light is in the middle or in the center of this sphere. Now, what is the surface area of this sphere? It's 4 pi r squared. So any sphere, its surface area is 4 pi r squared. So if we divide this luminous flux by the total area of the sphere, we get what is called what? The luminance. And it's gonna be here, its unit will be lumen per meter squared, because now we are measuring exactly what is the amount of luminous flux that each meter squared will receive. Each meter squared will receive. While here, the amount of luminous flux that a specific area, a specific direction will receive. Now, luminous intensity and illuminance, in some cases, they are equal and they mean the same thing. If I have here a wall, and this wall now, this candle now emits light on the wall. This wall now is perpendicular, as you see, 90 degrees with the what? With the lines of the light. At this case, if this wall is 1 meter away, of the candle, in this case only, the luminance, the illuminance, and the luminous intensity are the same. And also, if it's not 1 meter, you can find this formula, which is illuminance. It equals I, which is what? The luminous intensity is I. So the luminous intensity, which is I, over the radius squared. When does that, or when do we apply here? We apply this formula if the angle between the wall and the light beams is 90 degrees. So in this case, we apply this formula, which is E, illuminance, equals I, which is luminous intensity, over the radius squared. And the radius squared means the distance between the source of the light and the wall that we are measuring the luminous intensity on it. So you understand now what is luminous flux. And we said it is P, and its unit is lumen, and it is the amount of light, the total amount of light that comes from, or that a source of light emits. And we understand what is illuminance, and its unit is lux, and it equals the luminous flux, the total luminous flux over the area of the sphere, which is 4 pi r squared. And we understand what is luminous intensity, which unit is candela, and this is basic quantity. It's one of the basic quantities in physics. And we understand what is solid angle, and how or what, at what time the illuminance equal luminous intensity. And we understand also if it is perpendicular, if we are studying perpendicular walls, if we are studying the illuminance in them, at this case, we can apply this formula, which is illuminance E equals I, which is luminous intensity over the radius squared. In general, this one here, which is the sphere, here I have a sphere. This sphere now, if you open it, it's gonna be like exactly what? Like a rectangular. If you multiply then the length here, which is 2 pi r, if you multiply it by this height, which is 2r, you're gonna get what? You're gonna get 4 pi r squared, which is what? The total surface area of a sphere. And here we deal with the spheres because the source of light will be in the middle or in the center of the sphere, and it emits the light in all the directions, like there is a sphere of light is coming out of the source of light. So I hope you understand all these 3 points and the points or the main points that we have finished. Questions that are related to these parts will be solved on the quizzes.